So now that we've had our introduction to what series are, as well as determining the convergence or divergence of a series, for the next few sections we're going to be concerning ourselves with the very simple question, given a series, will it converge or will it diverge? Now we're going to be introducing a number of different tests to determine how to do so. The first one is going to be referred to as the integral test. So with that in mind, just a quick reminder, when we talk about a series, we're starting with a sum of a whole bunch of terms. In fact, because it goes on indefinitely, a series is sometimes known as an infinite sum. Now, this is not the first time in calculus that we have seen the capital sigma notation. As a reminder, and this is from all the way back in Calc 1, the definite integral from a to b of f of x dx is actually the limit of a Riemann sum. Oh yeah, hopping in our Wayback Machine here. Now, what this means for us, especially toward the end of Calc 1 when we were estimating the values of area under curves, we were doing so by taking a Riemann sum. Now with that in mind, when you consider the limit as n goes to infinity, then essentially what we have here is a series for all intents and purposes. So if delta x is not approaching 0, then the sum estimates. The value of the integral. Now that's if delta x is not approaching 0. Normally when we take the limit as n goes to infinity, it's going to work out just fine anyway. What I want to do is let delta x be equal to 1 and let b approach infinity. That is, for the improper integral over here, we'll just let that go on forever. And that means that the improper integral from a to infinity of f of x dx will be approximately equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I. Now again, we let delta x be equal to 1. Now with this in mind, this means that this series is going to be equal to f of a plus f of a plus 1 plus f of a plus 2, and basically that'll go on forever and ever and ever. Now it is because of that there is a strong correlation between an improper integral of a function and the sum of the corresponding series. Now, to give you a more realistic example, suppose that I wanted to consider the definite integral from 1 to infinity of 1 over x dx. This is saying take the reciprocal function and starting at x equals 1, determine all of the area that's contained over yonder. Now we know, based on some quick work here, for evaluating this improper integral, first we express the limit, the bound as a limit, and then we actually integrate. Limit is capital T, approaches infinity of the natural log of t minus the natural log of 1, which does eventually diverge. So the improper integral diverges. Now what we could also do is say, let's estimate the value of this integral by using a Riemann sum where the delta x is equal to 1. If we take a look at all of these areas, this area would be equal to a height of 1 times a length of 1. This rectangle would be a height of 1/2 and a length of 2. I know that this is 1/2 because at x equals 2, 1 over x gives me 1/2. The next rectangle, when x is 3, y is 1/3. For the next one, y is 1/4. Delta x is still 1. What you can see resulting here is the harmonic series exactly. Now, because of the overestimate in the integral, I know that these two things are not going to be equal to each other. Now, they're not equal to each other because we set up here they will be approximately equal to each other. The big important thing that we get out of this is, since the integral diverges, the series diverges as well. But we already knew that the harmonic series diverges from our last section. This is going to help motivate what is known as the integral test. The integral test states the following. Suppose that f is a continuous, positive, decreasing function on the interval from 1 to infinity. Let a sub n be equal to f of n. Terminology that we used in the previous section, we're saying that f is the generating function for the given series. Then the series from n equals 1 to infinity of a sub n is convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent as well. That is to say, if the integral converges, the series converges, and if the integral diverges, then the series diverges. This would be a much quicker check for something like the harmonic series, for example. Now, in the event that you don't have something like this, for example, if I wanted to talk about the series of 1 over, say, x minus 3 quantity cubed. This has a discontinuity at x equals 3. As a result, it's definitely not continuous on the interval from 1 to infinity. That just means that if I am going to set up a series like this, this should be an n, and this will be an n as well. However, if we were to talk about the function f of x equals 1 over x minus 3 quantity cubed, then you would have a discontinuity at x equals 3. So because of that, we definitely can't start the series at n equals 1, because after 1 it would go to 2, and then it would go to 3, and we have a discontinuity there. So as long as you're starting at a value of 4 or greater, you could still apply the integral test to what we're doing.